is quite nice, right? Well, anyways, Assalamualaikum and good morning everyone. Today, I'm presenting my journal title. So, the research is grounded in the environmental and industrial challenges of the 21st century, specifically focusing on the following areas: increasing demand for construction materials. With the global population exceeding 7 billion, there is a massive demand for buildings and housing, which has led to a depletion of natural materials used to make concrete. Environmental impact of plastic waste. Plastic are highly resistant to decomposition and can remain in the environment for hundreds of years, posing a significant risk to the ecosystem. Sustainability and resource conservation. The study aims to provide sustainable alternative for concrete components to maintain the continuity of natural sources and extend their shelf life. Previous research gaps. While many researchers have explored using polyethylene terephthalate or known as PET as a fiber in concrete, there is limited research specifically regarding its use as a partial replacement for fine aggregate, which is known as sand.
One to the primary material investigated in this research is polyethylene terephthalate, which is known as PET waste particles. What's the source? The PET was sourced from small and large plastic bottles of various sizes and colors purchased from local recycling factories. What about the processing? These bottles were minced and shredded using a special machine to achieve small diameters and a gradation similar to natural sand. What's the application? The processed PET particles were used as a partial replacement for fine aggregate, which is natural sand, in weight percentages of 5%, 7.5%, 10%, 12.5%, 15%, and 20%. Other components, which is the concrete mixture, also utilize ordinary Portland cement type 1, natural sand, maximum size of 4.75 mm as a reference fine aggregate, crushed natural stones, maximum size of 20 mm as a coarse aggregate, and lastly, liquid superplasticizer, modified polycarboxylate polymer to assist with workability.
A method for developing the sustainable material. The sustainability material in the study refers to polyethylene technology, PET, was particularly used as a material replacement for natural sand. The development process involved the following steps, such as sourcing. Sourcing is a small and large PET bottle of the various size and color. We collected from a local recycling factories and choppers. Shredding and mixing. The bottles were processing using a specialist shredder machine. This machine consists a hopper for input, a rotation shaft with a 9 moving blade, and 2 star blade for cutting. Shifting and gradation is a filter at the bottom, and the shredder machine was used to shift the plastic parts to ensure they reach the required gradation. The goal was to achieve extremely small diameter that could pass through sieve. Number 4 is making them close to the gradation of the natural sand. Integration this process of PET particles were then used to replace natural sand in concrete mixture at specific weight percentage, like such as 5%, 7.5%, 10%, 12.5%, and 12%. The type tests are used on the sustainability material. The research conducted various tests on about raw PET particles and the resulting construct mixture to evaluate their performance. Tests on raw PET particles safe and is used to ensure the particle mix the requirement for the sand under hierarchy and ASTM. And specification is specific gravity and absorption rate, performance to understand the physical properties of the PET particle compared to natural sand. Test on the fresh and highly concentrated slump test. Performance to evaluate the workability of the fresh concrete mixture. Comprehensive test conducted on the cut specimen at 7, 14 and 28 days. To measure how the material will be as a lot, splitting tensor stress test, performance on the slider specimen to determine the material resistant to tension. Flexural test conducted on the fringe specimen to evaluate the bending stress. Modulus of elasticity measure use the large cylinder to determine the thickness of the concrete. Energy absorption and energy strain test to analyze the ductility and energy storing capacity of the specimen. Dry density measurement performed to observe the weight reduction caused by the lightweight PET particle. Shrinkage and the expansion test conducted on sprint over 140 days to monitor volumetric change during and drying. Absorption test measure the rate at which a hardness concept absorb water. Ultrasonic pulse-velocity (UPV), a non-destructive test used to evaluate the overall quality, density, and the percent of void in the concrete.
Result analyzing from the test done. The study analyzed how varying percentage of PET waste 5% to 20% as a sand replacement affect concrete performance. Workability slump, concrete workability decrease as the PET content increase, especially 20% replacement lead to 62.5% reduction in slump compared to the reference mix, likely due to the larger surface area of PET particle requiring more water saturation. Dry density decreased as more PET was added because PET particles 1030 and are much lighter than natural sand. This makes the resulting concrete suitable for application where reducing that load is beneficial. Compressive strength increase for replacement ratio between 5% and 12.5%. The optimum percentage was 7.5%, which was 43.64% increase in strength at 28 days. However, strength began to decline once PET content exceeds 15%. Splitting tensile and flexural strength, both properties show improvement at lower replacement level. Splitting tensile strength peaked at 7.5 PET, while flexure strength also saw its highest increasement at the same 7.5% replacement level.
Sustainability concept in this research is built on two main pillars of environmental and resource management, waste management and environmental protection. Plastic waste, particularly PET, is highly resistant to natural decomposition and can persist in the environment for hundreds of years. By incorporating this waste into concrete, the study provides a method to rid the environment of harmful wastes that otherwise pose a future threat to the ecosystem. Conservation of natural resources. The construction industry is facing a depletion of natural materials like sand due to the massive demand for new buildings. Using PET waste as a partial replacement for fine aggregate, which is sand, serve to maintain its continuity for the longest possible period and extend the shelf life of its resources. Circular economy. The research aimed to transform a non-degradable waste product into a valuable construction material effectively creating a sustainable material that improve certain engineering properties of concrete while solving a waste disposal problem.
Source and processing. Raw material, cut waste, was sourced from small and large plastic bottles of various color and size collected from local recycling factories. Mixing and casting. Aggregate and fat waste were first dry mixed in an electric mixer, followed by the addition of cement, and finally water and substances were added gradually. Curing. Specimens were cast and placed at an interval of 7, 14 and 28 days to monitor property change.
Conclusion of the research. The research concludes that PET waste can effectively repurposed as a construction material, offering both environmental and structural benefits. Positive impact on strength. Replacing natural sand with PET particles improve the mechanical properties of concrete, which is compressive, tensile and flexible strength, as long as the replacement ratio remains below 15%. Optimal performance. The optimum replacement percentage was found to be 7.5%, which yielded the highest increment in strength, 43.64% for compression, 26.9% for splitting tensile, and 30.2% for flexural strength at 28 days. Physical property trends. As PET content increases, the density and ultrasonic pulse velocity decreases, making the concrete lighter and potentially useful for reducing dead loads in structures. Water absorption increases with higher PET content due to the irregular shape of the particles, creating more internal voids. Ductility and elasticity. The inclusion of PET waste reduces the modulus of elasticity, meaning the concrete becomes more flexible and deformable, and increases energy absorption and axial strain. Sustainability contribution. The application of this result in engineering works provides a dual benefit. It rids the environment of non-degradable harmful waste while simultaneously improving concrete properties and extending the life of natural source.